with that, let's get started, actually. Earl is the VP of Quantum Science at Riverlane. He's also a senior lecturer of quantum computing at University of Sheffield. This is from his Quantum Wizardry website, in case you haven't found that. And it's my pleasure to introduce Earl, our invited speaker for this session today, and he'll kick us off and set the tone for all the other great talks we have today. Please, Earl.
Thanks for the introduction. It's great to be here. So thanks to everyone who's got up so early to come for the 8 a.m. session. It's certainly the earliest that I've ever given a talk. Certainly the first session I've ever given a talk where I've not had breakfast yet. So I'm going to be talking about Riverlane's work on building hardware decoders. So this is all relating to an archive paper we put out last year. And I like to start the talks with this picture here, which is a picture of the first ASIC that we taped out for decoding. And you can't really see it very well here, but this ASIC is actually at the stall at the expo hall if you want to see it. So this is an old design of the ASIC that we taped out. It's not the one that I'm going to be presenting today, but I still like to start the talk with it. So it's very exciting to be the kind of start of this era of early fault-tolerant quantum computing, where we're really starting to see the first incredibly impressive error correction experiments. I'm just highlighting a few of them here: ETH Zurich, Google, Harvard. And something that all three of these experiments have in common is that they all did decoding in post-processing, so not in real time. They collected the data, they saved it somewhere, and then they decoded it. And in fact, in the case of the Google data, you can still go online today and get a copy of the data to decode it yourself. And so this is absolutely fine for a memory experiment. And in fact, decoding and post-processing also works for Clifford logic. So the requirement really is just that all of the gates that are implementing the QEC experiments are Clifford gates. And so if there's some kind of logical Pauli correction that your decoder is telling you to implement, you can propagate that through and kind of just toggle off different measurement outcomes. However, when we do non-Clifford gates is where we really start to get the requirement for fast real-time decoding. So I'm just going to have a few slides now to run through and give the whole talk a bit of motivation and context about how if you don't decode fast enough, you encounter what we call the backlog problem, which comes from this Barbara Terhal review paper. So we have some T-gate, let's say, some non-Clifford gate that we'd like to implement. And the standard textbook way of doing this nowadays is to consider doing it by teleportation using a magic state. So you might have some teleportation gadget that looks like this, where you've got to do a classically controlled S-gate conditioned on the outcome of this Z measurement. Often this is drawn so it looks like they're happening simultaneously, but in reality you need to have some kind of latency or lag between the measurement outcome and the Clifford correction itself. And I'm imagining that these are error-corrected qubits, logical qubits, which means that, in fact, I don't just want to take the raw outcomes from this measurement, I want to use the error-corrected outcomes. So before I can perform this classically controlled S-gate, I have to decode all of the syndrome data up to this point in time. And this leads to a backlog between the point in time which the decoder has got up to and where the algorithm has got up to. And we're imagining that in this period of time here, in this interval, we're still performing QEC to prevent the qubits from decohering, so we're still collecting syndrome data. So here I've kind of put a lower bound on what the amount of time is, assuming that the amount of time that it takes to decode, say, T amount of time worth of data, scales at least linearly with the amount of data that has kind of passed. So this was a reasonable assumption, and there are various ways that this can be broken nowadays. But up until, say, 2 years ago, all of the decoders that I was aware of took at least a linear amount of time to run. And this scaling constant f you can think of as being the ratio of the time it takes to decode per QEC cycle divided by the amount of time it takes to execute per QEC cycle. Okay, but the backlog problem really becomes pronounced and a real problem when we start to perform multiple T-gates in succession. So imagine now we've got a second T-gate, and I have to then say, hey, how much time does it take all of the data to decode all the data up to this point in time? Well, I have to look at the elapsed time, which will have a contribution that contains a term f times t, and multiply all of that time by f, and then do some subtractions, etc. The important thing is that you end up with a contribution that scales like f squared of t. And in fact, if I iterate this argument, then on the nth T-gate, I'll have a contribution that scales like f to the power of n. And so if f is a constant that's bigger than 1, you're in serious trouble, because now you've got an exponential slowdown in the rate at which you can compute. And so remember, this constant here, f, is the ratio of the time it takes to decode per cycle divided by the QEC cycle time. And so for superconducting qubits, we set this to be about 1 microsecond And so we're hoping that we can decode at a speed which is 1 QEC cycle per microsecond. There are various ways around the backlog problem, and when I was here at APS last year, I presented about our work on what we call, I'm not going to the next slide. I presented on our work on parallel window decoding, and there have been other works such as the sandwich decoder, and what these kind of parallelization methods do is they try and take all of the decoding data that you've got over time and break it up into chunks and process them in parallel. And what this means is that you can avoid this linear scaling which underpins the argument that I just gave you and avoid the backlog problem. But if you use these parallelization techniques, they come at a cost, which means that you have to slow down the logical clock speed of the quantum computer. And that's ideally not something that we would like to do. So these are kind of techniques of last resort. They're there for them if we need them. But ideally, we would just decode fast enough that we can use the more conventional way of keeping up with things in real time, so-called sliding window decoding. So the context for this talk, unlike the one that I gave last year, is that I don't want to do parallel window. I want to go at speed, which is 1 QEC cycle decoded per microsecond. So I'm sure many of you are experts on QEC, but let's just do the first review or recap on quantum error correction since we're kicking off the session today. So throughout this talk, I'm going to be thinking about the surface code. It's a 2D array of qubits where the yellow ones are data qubits and the gray are ancilla qubits helping me measure the checks. Red areas are ZZZ checks or ZZZ stabilizers, and blue objects represent XXXX checks. If we then ask what happens when we bit flip one of these qubits, if I have a single bit flip error, it will flip the values of the observables, the Z checks, adjacent to it. And so I will call these and illustrate them this way throughout the talk. I'll call them defects. So a defect is a change in the value of some stabilizer that you're measuring. So if I have a single X error, I'll get a pair of defects next to it. And if I have a string of X errors, then I'll see a pair of defects at the end of the string. And so really understanding this diagram gives you most of what you need to know about what the decoding problem is. It's about trying to find the shortest path between pairs of defects. And when there are more than pairs of defects, you're trying to cluster them up into groups of pairs such the sum of the distances between each of them is small. That's only part of the story because there are other types of errors other than just qubit errors. The actual measurement process itself can go wrong. And allowing for the possibility of a measurement error incorporates a third axis we can think of as being a time axis into the decoding problem. So every one of these vertical edges represents the defects that would occur if you had a measurement error in the process of measuring your checks. But this isn't really the gold standard for QEC. The gold standard nowadays is really circuit level noise. So here we want to consider the possibility that errors happen at any point during a circuit, which is responsible for extracting that syndrome. So here we have a kind of typical syndrome extraction circuit for measuring X, 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 X. And I've highlighted an error that could happen in the middle of this circuit. And when we allow for the possibility that errors happen mid-circuit, they lead to pairs of defects which aren't represented on that simple qubit graph that I showed you. So I'll be calling these hook errors throughout, the kind of extra errors that you can get which aren't really clearly qubit errors or measurement errors. And what these introduce are diagonal edges within this decoding graph. So one of the reasons why I'm taking a bit of effort and time here to explain the distinction between the kind of toy, what we call phenomenological noise models, and circuit level noise models, is that one of the things that our decoder did is that it was the first scalable hardware decoder that handled circuit level noise. And when we make some comparisons to other hardware decoders that are out there, I'll be contrasting the fact that they are presenting their benchmarks based on the easier noise model of phenomenological noise. Okay, so I thought this is probably primarily a physics audience, and maybe actually you don't know that much about what the difference is between, say, a hardware decoder and a software decoder is. So I'm also going to do a few slides just recapping the difference between building something in hardware and building something in software. So when we say that we build a hardware decoder, we're talking about programming at the level of elementary gates. So elementary operations like AND or NOT gates that are linked together to form a logic circuit, where we have some inputs which are really set to be voltages, and these voltages propagate through this circuit from left to right. So the voltages at the output ports never affect the input ports, so the logic is only ever flowing from left to right. And using some set of gates, you can realize any Boolean functions. But Boolean logic isn't really universal. So if you want to have a Turing machine, you need to do something else. And the thing that you have to do to get universal classical computing is you have to allow for the possibility that outputs kind of go backwards and become the inputs of some logic block again. And so you have logic that's kind of flowing from left to right and then cycling back around to the beginning of a logic block. However, these things, when you build them, they're actually analog components, right? The voltage propagates through and it has some kind of time delay in there. And each one of these components can take a different period of time for the signal to propagate through. And so what this means is that unless you do something else to discretize the system, it becomes very uncomfortable because you have to kind of think in an analog way. And so what we typically add is something here, which is a clock, a register, which loads the data from the left into here and then propagates it back around. But it only does this when the clock ticks. And so what this means is that it discretizes your logic. So here's a picture. I don't expect you to absorb everything that's going on, but it's just an illustration of many cycles, so many clock cycles, and then just the value of different voltages at various points inside some example circuit. And what you can see here is that there's some latency. There's something that changes like a reset or a clock event, and then the signal takes some amount of time to propagate to change some output value. And so here we can see the clock time has been set in such a way that in all of these examples, the signal has equilibrated before the next clock cycle has ticked. And so the way that you can think about it from a physics perspective is that you have a kind of physics system, and you have to wait for it to reach an equilibrium at the output port before you allow a clock tick. And so you've got to do a lot of analysis to figure out what is the worst case scenario in terms of the amount of time that might need to elapse. And this kind of tells us about two important features of doing things in hardware. One is that there are trade-offs that you have to think about, such as you can have quite a large logic block that does complex things between each clock tick, but there will be a trade-off. The bigger the logic block, the slower you can set the clock. But the bigger the logic block, the more work can be done in every single clock cycle. So these are careful things to consider when you're designing something in hardware. And the other point is determinism. So if engineered correctly, you can predict precisely to the exact number of clock cycles, and so how long your algorithm or your logic will take to compute, right? So this is really important in quantum computers where we're doing things in real time because we need all of our qubit fast feedback operations to be implemented in a perfectly synchronized fashion. So everything should work in a deterministic fashion. And this is one of the main things that's difficult to achieve if you were to, for example, be trying to decode using your laptop. So what does it mean on a kind of day-to-day basis? That's actually quite abstract, what I described in terms of logic circuits. The actual work that someone would do is they would write in some kind of human-readable language called a hardware description language, typically Verilog, which describes these logic circuits and registers in some fashion. And then this gets compiled down into the logic blocks. And then further, you can then send it either to an ASIC or an FPGA with a little bit of extra work for each of the routes. So if we convert this down the ASIC route, then what we end up with is a floor plan, literally a physical layout of all of the wires and all of the transistors required to fabricate that device. And by using industry standard tools, you can verify that all of the timing constraints are satisfied if you go up to some particular clock speed. So the advantage of an ASIC is that actually, once you've gone through the expensive process of designing it, the actual thing you end up with is quite small, typically quite fast and low power, and they're cheap to reproduce at scale once you've paid the initial outlay. But the disadvantage is that logic is fixed at fabrication. So if you want to innovate quickly and try out new ideas, or just deploy something to someone's lab, or have something that works alongside someone's control system, actually you probably want to be working with an FPGA. So this is the long-term option, and this is the kind of quick thing that you often do. So when you go to the FPGA route, what's happening here is that the FPGA has a whole bunch of components that are called lookup tables. And these lookup tables are logic blocks themselves with many inputs. but some of the inputs, you can send a certain signal into them that tells the rest of the logic block to behave like some specific Boolean function. So you can, for example, put a signal into a logic block that says, act like an AND gate. So this means that they're reconfigurable, but it means there's a lot of redundant circuitry in there. So these are relatively large, clunky things, and therefore they typically have much slower clock speeds. And so your algorithm will run at a slower speed on these devices. So that's my intro to hardware for you. Now let's go to the algorithm that was implemented on hardware. So we call our algorithm collision clustering. It's closely related to other clustering algorithms like union find. And so the way that I'm going to introduce it is by starting off by giving you like a high-level picture of what I mean by a clustering algorithm, then running through union find, then saying what's different about collision clustering and kind of running through the same example. So clustering decoding algorithms are ones that kind of have a two-step process. They first try to divide all of your defects up into suitable sized clusters, and then they find corrections that are supported on those clusters. And so here I've got two example clusters, and it's important that these clusters are what I call neutral. So neutral just means that there is a correction that you could perform supported within that cluster that would correct for those defects. So for the surface code, that means that there's either an even number of defects or the cluster touches a boundary where you compare things up to. So then we'll say that it's neutral. Once we found a neutral cluster, we can then try and find a correction supported on it. And assuming the cluster is sufficiently small, actually any correction on that cluster will be equivalent to another correction. It doesn't have to be the minimum weight one. And in fact, clustering in general is usually some approximation of finding the lowest weight error. So there's usually a little bit of loss in logical fidelity, but you make up for it in terms of having a much simpler algorithm that's easier to implement and typically runs faster. Yeah, so indeed, union find is almost linear running time in the number of defects, which sounds great, but actually isn't enough to avoid the backlog problem at arbitrary code distances. So even union find will have some finite code distance at which you encounter the backlog problem and have to play some other tricks to circumvent it. So here's my kind of simple example of how to think about union find. We're keeping it simple, so we're only looking at a 2D graph rather than a complex 3D graph with hook edges. The top left is the first panel, so these are the initial defects. Each of them is labeled with a G, sorry if it's not super visible, indicating that it should grow in the next step of the algorithm. So in the next step of the algorithm, each one of these vertices grows by half an edge, and we look for which defects have kind of collided together to form a cluster, which is neutral. And then I drop the G index. So there's a G here and a G here, but not on these two clusters because they're now neutral. So that means in the next step, these are not growing, but this cluster has grown and this cluster has grown. Okay? This cluster has hit the boundary, and so it's no longer going to grow. So now we've only got one cluster at the top that should grow in the next step. So this continues to grow, but actually something quite interesting happens in this particular example. This not neutral cluster with a single defect has collided with another cluster that has two defects. So the total cluster now has 3 defects in it, which means that it's not neutral. So this thing that you thought was resolved is not actually resolved, and you go to the next growth step, and it continues to grow. But what you see here now is that we've reached the final stage where there's really just 2 clusters, this large one and this small one here. And at this point, you can just find any correction. Sometimes this is called a peeling step. So the original union find paper from Delfos and Nickerson was really a kind of software decoder. The first paper that's really kicked off us thinking about hardware decoding was from Das et al. And so they gave an architecture for what an implementation of union find might look like. And I can say now, because I've mentioned how you go through the process of building a hardware decoder, what they did and didn't do. So they have like a high-level picture of what the architecture looks like and some models for predicting how it should perform. But they didn't have an implementation. They didn't have the hardware description language implemented. And so they couldn't, for example, verify that it met all of the timing constraints that you want to meet. So they don't know what clock speed, really, you could run it at. So you get some numbers in this paper, but the level of confidence that they're accurate or realizable is kind of unclear to me. So that's one thing to highlight. The other thing to highlight is how they actually store this information. And so the technique that they use is something called a spanning tree memory, which is really just an array of bits that labels where the defects are and also where the edges are. So I'm just showing you examples of what the configuration of the spanning tree memory is for the initial configuration and the final one. And so the thing to realize here is that because there's a lot of growth happening in these in union finds, there's a lot of reading and writing to this spanning tree memory. And so this is a potential bottleneck for the algorithm because, so you would refer to this as a memory-bound algorithm. And so what this means is that you expect that you'll be bottlenecked by the number of times that you have to read and write to memory, because you usually only do that, say, once per clock cycle, and you can fit a lot of logic in a clock cycle. So one of the questions we asked at Riverlane is there something similar to what you could do is there something similar to union find that you could do, but avoiding having quite so much logic in memory and quite so many read and write operations? And so what we arrived at is this thing that we call collision clustering. And so the idea is that instead of storing in memory the location of every single edge in your cluster, you instead just have a table that lists the location of every defect in terms of its coordinates and the radius that it has grown so far. And so for a 2D kind of slice of the surface code, these radiuses, these balls kind of form diamonds. And so if you look at this picture and you're Andrew Landau, you might say, hey, this looks a little bit like something I've seen in the historical literature, which was called expanding diamond decoders. And indeed, it does look quite similar to that, but there is a subtle difference. So in the greedy expanding diamond approaches, they're greedy, which means that as soon as they get a neutral cluster, they resolve it, they correct it. They don't allow for the possibility that that neutral cluster collides with a not neutral cluster and then continues to grow. And this is actually important because it means that the greedy expanding diamond decoders actually perform a bit worse in terms of logical fidelity than the non-greedy versions like collision clustering. So that's an important subtle distinction between the two, which my example nicely highlighted. Okay, so let's just run through the same example as union find a little bit. So we've got some initial configuration. Each one of our defects has a numerical label, and then we grow everything by half a step, so we get a half unit radius for each one of these vertices. And then we also have to ask, okay, where are the clusters? So initially, all the clusters are separate, they're individual defects. And then we have to ask, okay, so is this part of a cluster with this? And we do this by basically just checking the distance between every pair of defects and asking if the sum of the radii is less than the distances. So there's a good result of doing it this way and a bad result of doing it this way. So the good result is that it's relatively easy and fast to compute the distance between 2 points, right? And so actually, we can extend also this distance metric to account for hooks and all of those other features that we need for circuit level noise. Because it's a single arithmetic function, you can do it in a small number of clock cycles, much fewer than you would need if you were reading and writing to memory quite a lot. So this is all done using arithmetic logic. The thing that's bad about it is that now you have to look at all pairs, right? So you're going to have a scaling, a runtime scaling that is proportional or quadratic in the number of defects that you have. And the number of defects could be proportional to, say, d cubed. So you're going to have a worse asymptotic runtime, but you're going to have, you're going to have a worse asymptotic runtime, but you're going to have better constant factors in a sense. Sorry, I got backwards and forwards mixed up. Okay, so I won't go through every single step because you can probably imagine how it goes, but this is exactly the same example as we went through with union find, and I'm just showing you how the memory updates as the radius grows of the appropriate clusters, and then how this representation is just telling us which defects are parts of which clusters as part of a tree diagram. So throughout this presentation, I'm going to come back to this table to kind of compare and contrast our work with other people's. So the first comparison I want to make is with the Das et al. Paper. So they were looking at union find, which in theory should run in almost linear time, but their implementation is memory bound, and so that means that you can kind of think of that as entailing that there's a large constant factor in the running time. They only looked at, say, code capacity noise, and they didn't do a full implementation. So in contrast, we're looking at the collision clustering algorithm, which has a worse asymptotic runtime, but is very good in practice. And in fact, the asymptotic runtime that we observe is not as bad as this. There are many optimizations you can do to much improve this number. We looked at circuit level noise, and we implemented it both in FPGA and in ASIC using industry standard tools to be sure that we meet all of the timing constraints required. Okay, so now I'm going to present the FPGA implementation results. So for these results, what we were able to show is that if we synthesize it, we could validate that it meets all of the timing constraints up to a 400 megahertz clock. And so assuming that you have such a clock speed, a FPGA that can support that speed, which is fairly common, these are the results you get in terms of the decoding time, the amount of time it takes to execute per QEC cycle. And remember I said that I want this time to be less than 1 microsecond ideally. And so the 1 microsecond limit barrier is this dashed red line. So below this dashed red line, if you have a data point, it means that you could implement it using sliding window and run fast enough to avoid the backlog problem. The runtime depends on the amount of noise in the system, because that influences the number of defects that you have. The kind of typical benchmark we assume is, say, p equals 10 to the minus 3, and so that's the dark green curve down here. And what we see is that it stays below the red dashed line all the way up to distance 21. Yeah? So that's a good number, because around here, distance 21, 23, is where we reach something called the teraquop regime. So on the right-hand side, I'm showing what the logical error probability is as a function of the distance of this decoder. And we can see that if we want to get the error rate down to 10 to the minus 12, the teraquop regime, you need to get up to distance 23. So this FPGA is pretty close to meeting the teraquop regime requirements. And those are important because that's around the logical error rate you start to see lots of interesting quantum algorithms crop up. Like before the teraquop regime, there are not so many examples of nice quantum algorithms. So actually, the results are even better than what I'm showing you here. These are the results from the actual paper we put on the archive. But there's an archive update coming soon where actually we show we can get all the way up to distance 29. I've not presented the results today because these are shown in simulation rather than being fully implemented in our hardware description language. And so I didn't want to mix those two things up, but we're optimistic that we'll get all of these numbers up to distance 23 on an FPGA. So actually, the other important thing about our implementation is that it's very small and compact. It doesn't use very much memory or very much power. And so if you, say, implement it and you put it on, say, a Xilinx FPGA, which costs you less than 1,000K to buy, then what you find is that it uses less than 5% of all of the FPGA resources, even going all the way up to distance 21. So it's relatively small, and it can be synthesized alongside existing control electronics. And yeah. So I want to compare this with some of the other FPGA decoders out there. So the Helios decoder is a really interesting one that we're going to hear more about today. And so I'm going to comment on how our work compares to the work that was published on the archive last year for the Helios decoder. So Helios is really a distributed version of Union Find. So it's doing these growth steps in parallel. So it's using lots of memory as registers, but it's growing them all in parallel. So they all have their own dedicated local memory. In the paper put out last year, they only looked at phenomenological noise. So they didn't consider circuit level noise. And what this means is that you can't really make a kind of like with like comparison between our numbers and their numbers, but we'll try our best. And so making this generous assumption of phenomenological noise, what you find is that as you increase the code size, you use more and more resources up on your FPGA, and at some point you can't go any further on your FPGA. And so what they found is they could get all the way up to distance 21 on a fairly large, chunky FPGA, which I'm told would cost you about 20K. So it's all the resources on something expensive versus a small number of resources on a relatively modest FPGA. But actually, even when they get up to that code distance, it's still very, very fast. Yeah. Part of the reason it's fast is because it's looking at phenomenological noise, but the other reason is that it's just very highly parallelized. And so it's kind of quite funny, I find, that both of these decoders get up to distance 21, but for different reasons. Ours maxes out on bottlenecks on speed. This one bottlenecks out on FPGA resources. It would be interesting to know how it compares if you look at circuit level noise, and we may find out more about that in this session. So continuing the comparisons, adding in this extra row for the Helios decoder, we see that it also gets up to distance 21, but on a bigger FPGA, maxing out all the resources and only considering this toy model of noise. And again, also, we only know the results for an FPGA implementation. We don't know how it would perform if you went to an ASIC. And that's how I'm going to go on to next to present our results for our ASIC implementation. So again, the performance of your ASIC depends on how it's fabricated. So you have to assume some process or actually implement it. And as I mentioned at the beginning, the ASIC that we have taped out is an old design. It's not this design. But using the industry standard tools, we can validate what the performance would be, assuming some process node, which is kind of the size of the transistors effectively. So assuming a 12 nanometer FinFET process, what we find is that we can get up to distance 23 while staying below this 1 microsecond target that we set for ourselves. So you can get to a slightly larger distance because the ASIC can go a bit faster than an FPGA. You can clock it at a higher clock speed. And then the other important metrics for this ASIC is that it's very low power. It only uses 8 milliwatts. You can compare that to the power of a smartwatch in sleep mode. The actual size of our part of the ASIC, so excluding some of the I/O that you have to stick next to it, is less than the cross-section of a grain of rice. And to remind you what it is that we've done, we've worked out what the floor plan is for this ASIC, which gives you a map of where all of the wires and all of the transistors would sit if you fabricated it. And so that's how we know what the area would be and what the power consumption would be. So coming back to the comparison table, I'm just adding one extra entry here, which is to say that in our results, we have a small, compact, resource-efficient ASIC, which goes all the way up to distance 23 in less than a microsecond, and it's been verified using industry-standard tools. So just a tiny little bit, this is my last slide, a little bit on what next for Riverlane. So our core focus is on building our error correction for fault-tolerant quantum computers, and our next goal is to build a higher fidelity streaming quantum memory. So we use streaming real-time decoding to basically mean sliding window. So we're building a sliding window implementation. We also want it to be more parallelized, so we're going to trade a few kind of memory resources to gain some more speed. We also want to look at higher rates of error suppression. So, okay, union find is slightly less. Union find has a slightly worse logical fidelity than matching, and our decoder has exactly the same logical fidelity as a union find. But there's not much difference between them. But there is quite a lot of difference in logical fidelity if you can take account of hypergraph edges and other processes like leakage-aware decoding. So this is the direction that we're going in now. We're trying to push the logical fidelity, which will use some more resources on our FPGAs and ASICs. And then the third thing that we want to do is we're building out what we refer to as a universal interface. So in fact, the decoder is just a small part of the logic that you need to make error correction work. You need to be able to communicate the data throughout a kind of fabric of FPGAs, and you need to be able to do low latency integration to perform real-time experiments, including fast feedback. So we're building out all of that interface. So I'll just leave this last slide up here to show you some of the other talks that are happening this week presented by Riverlane people. In particular, Laura's one, where she's going to talk about the progress so far on integrating this decoder, the collision clustering decoder, with Rigetti qubits.
We have 3 minutes for questions for Earl. Francesco, please come set up. If you have a question, please come to the mic.
Thank you very much for your very interesting talk. And what kind of hardware structure did you design? Is it systolic array or some processor or kind of thing?
It's not a systolic array, no. It's a kind of custom processor.
Okay. And
yeah.
you cannot comment on more detail on that.
Well, the details in the paper, so it has a description of how the architecture works. So there's a set of finite state machines that pass messages between each other.
I see.
It's more like several processors than a systolic array.
Okay, yes. Just one more quick question. So what hardware resource limits the number of qubits implemented on that device, FPGA? What memory, logic, wire, what kind of resources
for us, we're not limited by memory.
Memory.
No, we're not limited by memory
Okay.
because it's very small in terms of memory.
So logic.
So we're limited by speed, effectively, at the moment.
Speed.
The Helios one, I believe, or we've got the expert in the audience, is limited in the number of lookup tables that it uses. Yeah.
Thank you very much.
you go.
Hi, Earl. Very nice talk. Thanks. I'm Yu from Yale University.
Yes.
And I have a question regarding your you speaking of leakage-aware decoding at the very end. Could you elaborate on that?
Yeah, we're going to share a leakage-aware decoder with the world at some point this year. So
Okay.
by the end of this year.
Yeah. Thank you.
All right. That was a great question, actually. And we have another minute of questions I'm going to ask. I can listen to Earl talk for a long time. But quick question. So you've been nicely breaking it into quantum memory experiments. But
Yeah.
once you do logical operations on these memories, the decoder graph, do you have to tape out new silicon, or how's that going to work?
Yeah.
Thank you.
Yeah, so at the moment, there's some reconfigurability, so you can tape out a single ASIC and you can change the size of a memory experiment, but a single ASIC doesn't support multiple types of experiments at the moment. So that's one of the other things that we're working on, is figuring out how reconfigurable every module has to be versus how much kind of we could solve things with data movement.
Right. And if the community converges on surface codes, then you can just give them out to everybody. But if
Yes, so there are other things that are not surface codes.
Right.
So yeah, we also have some work that should come out this year on belief propagation decoders. So kind of following a general process that we have. First, we do everything in software. So we're coming up with some kind of different ways of doing belief propagation that we think will be generally applicable across all codes. And so we're going to release the software decoder at some point this year, and then we're going to figure out if we want to put it into hardware or not. We've not committed yet.
Awesome. That's really exciting. Let's thank Earl again. Thank you.